Thanks to the organizers for the invitation. It's always great to be at Simon's. So today I'll be talking about a relatively new batch dynamic model, except combined with asynchronous reads, as it says on the slides. So this is joint work with a number of wonderful collaborators. So you know Julian and Igor, and Do-Hyun is an undergrad at Yale. Okay, so this is currently ongoing work. I'm going to be talking about the paper that introduced this model, and then I'll briefly touch on some ongoing work. Okay, so to start, the classic dynamic model is the sequential dynamic model. So in the case of graphs, what you have are edge insertions and deletions as your updates. And these updates arrive sequentially. So you get one update at a time, one after the other. So you can see in this animation, there's some edge deletions that occur, as well as edge insertions that get inserted. Okay, so the goal of dynamic algorithms is to maintain some form of property after you do the updates. So for graphs, for example, maybe you want to maintain a matching after edge insertions, edge deletions. So you want to maintain some form of a graph property after every update. So there's many different types of variants of dynamic graph models. So I'm going to briefly go over this, and then I'll describe our variant. The variants for dynamic graph models beyond the sequential classic model involve a number of things. So the first thing is, how do you represent your graph in your machine? So you can represent your graph in one machine. So you can store your entire graph in one machine in shared memory parallelism. Or you can distribute your graph across many machines. So we have already heard about distributed algorithms today. And you can use different kinds of resources to process your graph. So you can use multiple cores on one machine. So this is shared memory parallelism. And your multiple cores would be processing this graph in parallel. Or if your graph is distributed across many machines, you would instead have a communication network over these machines while processing your graph. When you're talking about dynamic graph algorithms, you can have multiple ways to give your dynamic updates beyond just one update at a time. So some of these ways are, you can have batches of multiple updates that are given to your graph at the same time. So this is a batch dynamic model, which I'll talk about shortly. Or in the streaming setting, you can have a stream of updates. And these updates just occur, and you can only store a small number of these updates at a time. And then finally, you can have different adversarial models. So your adversaries could be adaptive, so they can see your previous outputs or even internal states. Or they could be oblivious, so they can't see the internal states of your algorithm. They can't see your previous outputs when they're deciding your next updates. And even there are additional constraints, such as privacy violations. If you work in the differential privacy setting, there's various adversarial models in that setting as well. Okay, so just to give a bit of detail in each of these variants of dynamic graphs, as I mentioned, you can either have one machine or multiple machines. For this presentation, I'll focus on one machine. So I'll be focusing on shared memory parallelism. Okay, so in terms of shared memory parallelism, you have multiple cores and processors which operate on a single shared memory. Okay, I'm sure everybody here has seen some form of this picture before. So you have cores, which are your processing units, and they read and write to the same shared memory. Okay, so the model that we generally care about when we're talking about shared memory parallelism is the shared memory work span model. So you have work, which is the total number of operations, and then span, which is the longest chain of sequential dependencies in your algorithm. So the batch dynamic model is one form of model for representing dynamic updates. So in this model, you have batches of multiple updates that are given to your graph at the same time. So here, you can see an original graph on the left. So that is your graph at time I. And then you're given some series of edge insertions and edge deletions. So in this case, you can consider the dotted lines to be edge deletions, and then the solid lines to be edge insertions. So given this entire batch, you apply this entire batch of updates on your graph. So the dotted lines are deleted, the solid lines are inserted into the graph. So let's talk about this in a bit more detail. So what do you want to do here? As in the sequential case, you want to maintain some form of graph property after your batch of updates. So suppose you want to count the number of triangles in your graph. In your initial graph GI, you have 5 triangles. Now you have a series of edge insertions, edge deletions. You apply it to your graph, so now you have this new graph with some of the edges deleted, some edges inserted. And you want to maintain an updated number of triangles in this new graph. So in this example, the updated number of triangles you have is 4. Okay, same as the sequential case, except now you get a batch of updates. So the nice thing about getting a batch of updates is that you can process this set of updates using parallelism. So it's more conducive to using shared memory or distributed parallelism when you're trying to find these graph properties. So it's more conducive to using parallelism than getting updates one by one. So that is the power of this model. And there are many works in the batch dynamic model. So this is a small sampling of the works that exist in the batch dynamic model. There are quite a few recent works even on this model. Okay, and this list is, of course, biased towards graphs, since I'll be talking about graphs here. But there are also a lot of works that are not just in graphs. Okay, so far, what I've talked about are doing updates on graphs. So you have some updates on graphs, and you're maintaining some form of graph property after every update. So now the question is, how do we incorporate reads within these updates? Yes. Yeah.
Do I understand correctly that the correctness condition here is that the batches are not overlapping, and as soon as you have processed the entire batch, the property should, your algorithm should count appropriately, should have the property that you have. What's your correctness property?
Yes. Okay, that's a good question. So there's
Can you summarize
2
questions?
questions. Yeah. So the questions basically can be decomposed into 2 parts. So the first part is, well, what are the conditions on the batch? So what are the correctness conditions on the batch of updates? And the second is, what are the correctness conditions for updating the graph property after that batch of updates? So the first question, the correctness condition on the batch of updates is that the updates are just unique and they're over edges that either do not exist or exist. So if you're deleting edges, you're only considering deleting edges that exist in the graph. If you're inserting edges, you're inserting edges which don't exist in the graph. Of course, if neither of those conditions hold, you can just pre-process your batch to get rid of those useless updates. So that's a condition on the batch of updates. The correctness condition for the graph property is, after you process your batch of updates, you should just give a correct property for the graph in the new graph that consists of all the insertions and deletions that occurred in the batch. So the correctness condition is basically just you want to maintain a correct graph property after processing fully each batch of updates.
But the reads that you are going to bring now
Yes.
to the picture, do they occur right after the batch has been processed, or can be concurrent with the batch, the update, with the updates that the batch contain? The batch contains.
Yes. Let me quickly bring back my slides. I'm not sure why PowerPoint decided to quit. So that is a good question, which I'll talk about as I'm talking about how do we incorporate reads.
Thank you.
Yes, because obviously that's not an easy question. Otherwise, we wouldn't have a paper solving the issue. And just like you said, the issue with reads is that we don't want reads to necessarily occur while you're processing the batch, because that could lead to incorrect behavior. So I'll actually talk about it a little bit more as I'm talking about this model. Yeah. Any other questions? Okay. So let me jump into how do we incorporate reads. So far, what I've discussed is only updates. So you have some number of updates, and then you process the updates in your graph, and then you maintain your graph property after you process the updates. So far, I haven't talked at all about how to do reads. So easiest way you can do reads is you can just perform all your reads after you process the graph, after each batch of updates. So you can process your graph, get your new graph property. The new graph property could include a set of reads on each node of the graph. So it doesn't have to be just something like counting number of triangles. Maybe you want to query each node of the graph for some property. So you can do this after you process the entire batch of updates. Now, the problem with that is, imagine if you're looking at some web system and it does this every single time you want to see an update to your website. Obviously, that's going to be very high latency. And real life situations don't really allow for such high latency when you're trying to view an updated, say, website. Okay, so here are some examples of real life situations where you want lower latency reads than writes. Okay, so websites often have a front end that refreshes whenever you want to refresh it, while the back end produces more challenging changes. So if you want to make a greater change to your database back end, often the database front end doesn't reflect your changes as you're doing them. It reflects some stable state of your database. Okay, some other examples are often people want to produce live statistics of whatever you're looking at. Okay, so whenever you have a live sporting event, et cetera, companies like Facebook probably want live statistics of their user base, et cetera. Usually, you always want to see the live statistics, even if the live statistics doesn't always include all of your current changes. So you can process your changes in the background, but you always want to see some form of statistics. Okay, some other examples are search engine results. So as we know, search engines don't update instantaneously. They update on some snapshot of the web, but you always want to get results. And then, of course, social media websites often do updates in the background, but you always see some front end when you view it. Okay? And there are many more examples of situations where you want low latency reads while your high latency updates are performing in the background. Okay? So because of these reasons, it's not necessarily a good thing to just leave all of your reads at the end of your batch, because that means you're going to be waiting a long time for your reads when you really shouldn't be. Okay, so that is the motivation for this model that we say it's pretty much between a fully concurrent model and the synchronous batch dynamic model. So this is a parallel batch dynamic model with asynchronous reads. So what does this mean? This means that we have updates, which are part of your parallel batch dynamic model. And in addition to that, you also have reads on the state of your graph, of your data set. Okay? So the updates are given as batches and processed synchronously. So this is the same thing as the original parallel batch dynamic model. Updates are just parallel, processed in batches, and they're processed synchronously. The difference here is reads are processed asynchronously. Okay? And we try to process them as soon as possible. So the key here is as possible, because I'm going to show you some examples where we don't necessarily want to process the reads as soon as you get them. We want some algorithm to process them in a safe way. And specifically, what we mean by safety is we want the reads to satisfy linearizability. So we want them to satisfy the condition that's necessary for concurrency. Okay? And a desirable property is we want reads to be lock-free. So this is not required, but is desirable. Yes, Kuba first. Yeah.
I'm wondering, so when you say read satisfy linearizability, this means that each read gets the state either before a given update has started and after it has finished. Mm-hmm. There is no notion of like partially applying an update, right?
Yes, you can assume an update is an atomic operation. So it's linearizable with respect to any atomic update in your batch.
If my update was ordered, like here is a batch of updates,
yeah,
And I said, I'm fine with the result that applies a prefix of it. Would that be would that make things easier? Because it feels like that's also reasonable, right? To assume
Yeah, that's reasonable.
Like, would it make anything easier, or is this very different from what you're studying?
Yeah, I believe it would make something easier if you assume an order of the updates in your batch. So we don't assume an order of the updates in our batch. It's some linearization of the updates as long as you assume each update is atomic. Yeah, so assuming some order and assuming your reads occur after some fixed prefix of the order would make it a bit easier. Mm-hmm. Yes?
Wait, as a clarification, when you say the update, you mean the entire batch occurs atomically, or you mean individual things
Yes.
come in some order and
Okay.
the reads are stuck in?
Good. So each individual update is atomic,
I see.
but we don't assume a fixed order on the batch.
I see. So doing this would be then harder, right? Because that's a specific ordering, whereas this would allow arbitrary ordering.
That's fair. It depends. I guess when you have a specific ordering, the assumptions, the requirements for correctness is more stringent. So it's easier to rule out algorithms that don't work.
I see.
Whereas if
Sure,
you have,
it's harder
if
to
you
design
don't
an
have,
algorithm that does work.
that's yeah, that's right.
May I also
Got it.
ask something?
Yes.
So here you have threads that execute concurrently the batch of updates and other threads that execute reads. So the model is not the standard one, right? Because you have also, or is it that
yes.
every thread executes one update and therefore the model is the standard asynchronous shared memory model that the PODCI people are aware of?
Yes. Yes, that is a good point.
Could you try to summarize the question or?
Right, and let me try to summarize the question to see if I completely understand this correctly. So the question is, for the parallel batch dynamic model with asynchronous reads, we assume there are some threads that are doing the synchronous updates, and additionally some additional threads that do the asynchronous reads. So that is a different model than the standard concurrent model where every thread can perform any concurrent operation. Is that the correct?
Also, I try to understand if it is one distinct thread that executes an update, or if you can have multiple threads to execute the update just to speed up the update.
Yes. Yes. Okay. So the additional part of the question is whether you can use multiple threads to speed up the update. And yes, let me answer the second part first. You can definitely have multiple threads to speed up the update. The updates are processed synchronously, but they're processed in parallel. So you can have multiple threads process your entire batch of updates just in parallel. Regarding whether you need to partition your threads into update threads and then read threads, this is how we do it for the experiments. There could be more complicated scheduling systems where you don't necessarily need to do that. The model doesn't actually handle the scheduling part of scheduling threads for the synchronous updates versus the threads that do the reads. The simplest way to do it in experiments, which is what we did, is assign some threads to do the synchronous updates, and then other threads will just be pure read threads, and they're assigned to do the concurrent reads. Yeah. Any other questions?
So an example of read here, like
Sure.
you're counting the number of triangles in the graph, right? That is an example.
Yes, that's an example of a read.
So if you have
That's
a
right.
batch of some insertion and deletion, just for clarification. So if you have a bunch of read requests are also coming, those are asynchronous.
Okay.
I mean, number of triangles, that answer will differ based on when you choose to answer the query, and also what order you do the batch updates in that batch.
Okay, so the question is, when you have a read such as triangle counting, doesn't the result that you return depend on the order of updates you have in the batch, etc., or when you choose to do the read in the middle of your batch? Is that a good summarization of the question? So this is going a little bit more sneak peek into our results. So it is dependent. But we allow everything as long as it's linearizable. So you could be reading triangles in the middle of your batch, as long as you're reading triangles at a point that is linearizable with your atomic updates. So it's fine. I'll explain a bit more about how we measure, say, approximation factors and accuracy a bit later if you're doing that. But it's fine as long as it's linearizable. Okay, great. So let me move on to a concrete example, since a lot of these questions ask about details that will probably be a bit more clear as I go through a case study. So the case study I'm going to go over is what's called a K-core decomposition problem. And the way we do this is that we turn a parallel batch dynamic algorithm into one that can handle asynchronous reads. So we do this via a pretty a novel technique that I think could be applied pretty broadly to other problems as well. Okay, so let me first quickly talk about the K-core decomposition problem. Okay, so the K-core decomposition problem is a very well-motivated problem that talks about how important an individual is in your network. So for example, some amount of important individuals are influencers in the social network, super spreaders in a disease network, or global hubs in a graph of international flights. Okay, so important individuals are generally connected to other important individuals. So we can see an example here. So on the left, even though the middle node has high degree, it's not really connected to other important individuals. In fact, it's connected to a bunch of singletons, which means that it's probably a poorly connected node in general. Whereas this middle node on the right is connected to a lot of other well-connected individuals. So it tends to be more of a central part of your network because it's connected to more well-connected nodes. Okay, so basically cores intuitively measure this importance in your graph. So everybody starts off in one core. Okay, so as long as you have degree greater than 0, you're part of a one core. And then two cores are contain individuals who are slightly more important than individuals on the one core. So individuals who stay in the one core are more on the periphery of your network. And then three cores are even more important. So people in the three core are even more central to your network. Okay, so like every other paper, we're going to use n to denote the number of nodes in your network and the number of edges. So this is the definition, the formal definition of a K-core. So the formal definition of K-core is a maximal induced subgraph where each vertex has degree at least k. So there's a unique subgraph for every node that determines your K, not every node. There's a unique subgraph for every graph, every input graph. And this is your unique K-core for every distinct k, because you're looking at the maximal induced subgraph. Okay, so some questions are, at least for this definition, the subgraph doesn't have to be connected. It could be disconnected. That's why it's unique. Okay. And the core number of every node V is the maximum value k, where V is in the K-core. So the core number of node V is the maximum value k, where the K-core includes V. Okay, so the core number for every node basically gives you some number determining the importance of that node in your network. And this is pretty well studied in databases, data mining, ML communities, and is gaining more popularity also in the theory community. And one characteristic, which I already pointed out in the previous example, is that large degree doesn't necessarily mean large core number. Okay, and you can use this to speed up algorithms like triangle counting, clustering, etc. And a straightforward extension of this exact K-core decomposition definition is you can also obtain approximate core numbers. Okay, so pretty straightforward extension of your exact core definition. And there is one unique K-core decomposition for every input graph. Okay, so I'm going to go over this previous work briefly just to illustrate an example of what might be difficult when you're trying to put in asynchronous reads. So it's not terribly important to understand the entire algorithm, but I do want to illustrate it just to give you an example of what makes asynchronous reads difficult. Okay, so in this previous paper, we used what's called a parallel level data structure to obtain approximate core numbers for your nodes. On a very high level, the algorithm works by placing nodes in a level data structure and then moving the nodes up and down the level data structure according to some rules. And then the final level that each node ends up on gives you an approximation of the core number. Okay, so here you have some O of log n levels. All of the nodes initially start off at the bottom, and then suppose that all of these red edges are edge insertions. So it's a batch of edge insertions to your graph. Now, you move up a node if the induced degree in the same and higher level neighbors is greater than 2.1 times 1 plus eta. So eta is just some constant factor in between 0 and 1. Okay? So if each of these induced degrees is greater than 2.1 times 1 plus eta, then you move the nodes up. So here are the induced degrees. Okay. Now, suppose that eta equals 0.1, you move up these nodes. So all of these nodes remain active, and the blue nodes become inactive. So you keep performing this step. So you keep moving up the nodes as long as the induced active degree is large enough. Okay. So you update the induced active degree here and here. And then if it exceeds the threshold, you keep on moving it up. So in this instance, this is a pretty dense graph. So you keep on moving it up until it reaches the last level. So the key observation that we have here is vertices in the highest level have core numbers approximately equal to the cutoff. Now, in order to get more accurate approximations on your core numbers, you just stack multiple of these groups of levels on top of each other, each with an exponentially increasing cutoff number. Okay? And then your final approximation is the largest cutoff, where the vertex is above the topmost level of that cutoff. Okay, so here are some previous theoretical guarantees. It's work efficient, so it's best. It takes amount of work that's asymptotically the same as the best known sequential dynamic algorithm, and it has polylog depth. So the question here is why can we not just directly add asynchronous reads? Okay, and just as a brief preview, the problem is we need to read the final levels of these nodes to get an approximation of the core number. But if you just read the nodes as it's moving up the levels, it could be in any intermediate level that would not occur if you assume an update is atomic. Okay? If you have atomic updates, it will only read the beginning level and the final level. It will not see any of the intermediate levels as you're moving the nodes up. Okay, so let me just summarize that intuition. So a number of problems is, what if we just want to query the state? So some approximate core number whenever we want. Not at the end of the update, we just want the approximate core number when we want it. Maybe in the middle of a batch of updates. So this previous parallel LDS algorithm doesn't have a built-in read mechanism. So option A is, of course, you can wait until the entire batch is done, and then do a batch of reads all at the same time. So every time a read comes in, you add it to some queue, and you wait until the entire batch is done, and then you perform all the reads in your queue. Okay, so what it will look like is this. You have an update batch, and then you have a read batch, and then you have an update batch. Okay, so there are a number of things that are wrong with this, which is it simultaneously makes your updates slow as well as your reads slow. Okay, because your reads have to wait for your update batch to be finished, and then your next update batch has to wait until your reads are finished. So this is basically gives you the worst of both worlds. Okay, and in particular, your reads now have high latency. Okay, option B, you just read without synchronization. And as I mentioned, this is not linearizable as when you're assuming the updates are atomic. Yes, Cuba.
So maybe I misunderstand, but if
Yes.
an update changes the core number of a vertex from A to B,
Yes.
and I think there is a subset of this update that actually changes it to any intermediate value. So basically, like it feels like by being creative, saying, well, there must be existentially, there must be a subset of the updates that actually cause this, yields this core number. I mean, I don't know if the idea is clear.
It has to be consistent across.
Yeah,
Yes, it has to be
across all of
consistent.
them, right? You need to give one linearized order of all of the
Okay, so
updates.
that
Yes.
so the reads are also in batches, and you want to have is that what?
Yes, the reads could happen in batches,
Okay, so
which is
that-
what
okay,
this is
so-
going to show.
Okay, so
Yes.
basically,
So-
if the reads
Yes.
were not batched, this could have been an option.
Yes,
But
this
because
could-
it's batched, okay.
Yes, this could be okay if it's one read at a time, but the example I'm going to show is when you have read batches and it's not consistent across states. Good. Yes, great question. Yes.
Yeah, what prevents you from doing the following trivial thing that just keep 2 copies of the graph?
Oh,
While you
yes.
use the other one, you answer from the original one, and once you end, you just switch between.
You could do that. You could do that. That increases space. So you have 2x space.
No?
It is a trivial solution. So there's 2 answers to this. So this is a good suggestion, and in fact, this is there are some papers that actually just do this. they just keep 2 different copies and then read between 2 different copies and then moves on and then updates the old copy. Yeah. So there are some solutions that actually do this. There are 2 problems with this. The first one is increases the space, is 2x space. Whereas a lot of the results here, or our paper, uses less than 2x space. So that's the first thing. The second thing is the problem with keeping multiple copies is that one of your copies is going to be pretty stale by the end of the time that you update your newer copy. So it is linearizable, it is correct, but there is some form of staleness if you are using only an old copy without taking into account any of the new copy. So the advantage of having some of the new copy is that some of your updates will be less stale than others. But if you read off of only your old copy, all of your reads will be stale.
Divide the batches into sub-batches so that they are not that scale.
Yeah, potentially. Potentially, all good ideas. I encourage you all to write your ideas into papers. Yes, great questions. Okay, so going back to the issue here. So the reads, let's just say you have all these reads and the reads occur at the same time. You just make it occur whenever you want. Now, the problem here is if you have an update, U, that causes other vertices to be updated. So you have this U, and it causes this V and this W to be updated, which it will occur. So in this level graph, this movement of this node up to here will cause these 2 nodes to move up here. Okay, so this is a dependency graph. So we can have a dependency acyclic graph, dependency DAG, where we can show that V and W depends on the movement of U. And specifically, U's move caused W to move. So now, exactly as we discussed in the previous question, we have 2 reads now. 2 asynchronous reads that occur at almost the same time. So you have a read of U, and you have a read of W. Now the problem here is you want these to be consistent, and this is incorrect. If you read one of these nodes, say U, to be at level 3, while the other node is at level 5, which is an intermediate level. So what you want is a consistent representation of U and W. With this update, U and W's level should have changed, whereas here, one of them changed to the new level, while the other one was still in an intermediate level. So in some sequential execution, UVW will move to their new levels atomically. And there you wouldn't get a combination of reads that give you a new level and then reads that give you some intermediate level at the same time. Okay? Any questions about this example? So the problem here is these reads do not give you a linearizable state because some of them read your new level where others read some intermediate level or some old level.
So all your
Yes.
in this model, reads are always just reading one word.
Yes. You can extend the model to read more than one word. But for this example, yes, where each read is only reading one value, which is your core number. So one word.
But if you can read more than one word, then you almost have to take a snapshot, right? Atomic
Yes.
snapshot.
Yes, that's true. That's true. That makes it more complicated, yes. Yeah, I guess in some sense, what you said is exactly correct. Because if I allowed a read to say, read the entire graph, then you have to have a snapshot. So if you allow for reads to read more than one word, you could potentially need to read the entire graph. At that point, you need a snapshot of your graph. So you're exactly right there. For the purposes of this, you can assume reads only read one word. So for all the examples that we have in this model, they only read one word. OK, so let me move on, since I'm going a bit over time. So option C is to do what we're going to suggest in this paper, which is you want asynchronous reads with linearizability combined with synchronous updates. OK, so we're going to use this concept of using the dependency graph. And we think we can apply this to more than just this algorithm. So we use this dependency graph, and we want to do our synchronization using this dependency graph. Okay? So when we get updates, we update the dependency graph. So each update will cause some nodes to move, which will cause other nodes to move, so the graph will get larger as we get updates. So we want to maintain all dependencies that we have while we're processing these updates. And then once you're doing the reads, you want the reads to traverse the dependency graph. So you want these reads to consult this dependency graph that you have before you return your values. OK, so basically, I'm not going to go into the details because I'm a bit low on time. But the intuition is you want your reads to check whether there are updates that are occurring earlier in your dependency graph that you depend on. And you don't want to return a value until those updates are resolved. OK? So in summary, you want your updates to record the dependencies in your dependency graph. And whenever you're doing a particular read of a node, you want to return some linearizable result based on the dependencies that you read. OK. So the last few slides, we're just going to show some experiments. So these are pretty standard machines that we use from GCP. And we show some massive improvements in read latency across the experiments. So here are some summary of all the graphs that we tested. These are all real-world graphs you obtain from pretty standard repositories. So you can see some of them are pretty dense. So for the dense ones, the maximum K for any K core is pretty large. Some of them are pretty sparse, with a max K core of 2, 3, et cetera. Very sparse graphs. OK, and we test our new data structure with asynchronous reads. We call this cPLDS for concurrent PLDS, with two benchmarks, which are synchronous reads. Sync reads is you put all your reads in one batch, and you read it after you process your batch, your update batch. And then non-sync, also very simple. You do your reads immediately. So you perform your read immediately when it's queried. It applies immediately because you read the current level of the node. OK? No locks, nothing. Just read the current level. OK, so the read latency. So I'm going to show the graph for the read latency first. So the read latency, we get 10 to the 5 orders of magnitude better than our synchronized reads. So this is synchronized reads. Updates take pretty long, so the latency is the worst for synchronized reads. The latency for non-synchronized reads is the best, but we obtain within a 3.2x factor of the non-synchronized reads. Yes, Kuba?
You can make this arbitrarily large by making update batches larger.
Yes.
How large were the
Yeah, good question. Good question. Okay, so if you look at our paper, we do test different sizes of batches, but we do 10 to the 6 update batches. Yes. So this is less than 10 to the 6, it's 10 to the 5x, 10 to the 5x better, but we use 10 to the 6 batches. Yes, good question. Okay, so this is a latency, average latency. Now we have throughput. And then throughput is the best would be sync reads, although all the throughputs are approximately the same. So throughput, either non-sync or sync reads should be best. So we're within 1.4x of the better of the two. Okay, so our read throughput is quite good still. Now this is the approximation error. So approximation error, we basically compare for every update. We give it, we compare it to the approximation that we get after performing the update and the approximation before performing the update, and we take the best out of the two. Okay, so it just basically says we get some approximation in between when the update was applied and when the update ends. So we take the best off of the approximation for the state after the update and state before the update. Okay, so using this approximation method, we get within 1.15 of sync reads. So sync reads is always going to be correct because you perform the entire update. So sync reads will always give you the best approximation. And then we obtain the 52x better than non-sync.
We're going quite a lot here.
Yes, and now we're done. So the new ongoing work we have is we're trying to apply this for skip lists, and this is with the undergrad Do-Hyun at Yale. Okay, that's it.
One question?
So when we go to the streaming data, what changes? I mean, what is the correctness condition? How do you formulate your system?
When you're considering streaming updates instead of batch updates? Yeah, that's a good question. We haven't looked at streaming updates. But generally, the constraint for the streaming community is not update time, it's more in terms of space. So you want to keep as few of the updates from your stream as possible when you want to perform your update.
There are no streaming results,
Nope.
Results about streaming in the paper.
Yeah, no, there are no streaming results. This is
Sorry,
purely for the
because
batch dynamic.
You mentioned streaming at the beginning, and I thought that
Ah,
there were
yes.
results in the paper.
Yes. The streaming is another model for dynamic updates. This only focuses on the parallel batch dynamic model.
Okay, good.
Yeah.
All right, let's thank Quanquan again. So we're free for 2 for lunch. If you're not been to Simon's before, if you walk southwest, there's a whole ton of student-oriented places where you can get, lunch, take out and sit, find somewhere nice to sit.